Bismillahirrahmanirrahim. I am Professor Jamil and you are watching YouTube channel. Today we are going to solve a question on Laplace transform of the nth derivative of some function. And here is your question. Find value of Laplace transform of the nth derivative of the function f for non-negative integer n. The order of the derivative is non-negative integer, mean n could be 0, 1, 2, 3 and so on. Let's do this for these values of n. So here your answer goes. ANS for n0 implies Laplace transform is d0 by dt0. And this 0 means 0th order of derivative, that means no derivative. So it is Laplace transform of f, and f is a function of t. This is visible from this given question. You are differentiating the function f with respect to t. This means f is a function of t, and that has been written here. So for n equal to 0, this Laplace transform of the nth derivative means a simple Laplace transform. Next, you may name this as equation number 1. Next, for n equal to 1, this implies Laplace transform of d1f by dt1, right? And you may name it as Laplace transform of, this is first derivative of f, and you can write it in terms of prime notation. This prime means differentiation with respect to t. And this may be simplified so that this turns into something like this. And you may use the value for L. This is Laplace transform operator, which is an integral operator, and integration will be over t because your function depends on t, whose transform is required. You require Laplace transform of f prime, and f prime depends on t. So t will be the variable of integration, and in Laplace transform, integration is from 0 to infinity. Then there is a kernel for the Laplace transform, which is e to the power minus st, one old variable which is t, and s1 is new variable, into the function whose Laplace transform is required, mean f prime in this case now. Okay. Now look at this in last right hand side. Left hand side, right hand side, and this is right hand side. This is a definite integral which contains product of two factors. And when there is a product of two factors in the integrand, then it is common, or it is the first option that you should think about integration by parts. So when you do integration by parts, the function whose derivative is present in the integrand, that is always selected as the second function. So the other factor will be taken as the first function or first factor, and let's integrate it with respect to, integrate by parts. Integrate by parts. And of course, your integration is with respect to the variable t. So let's integrate. First function as it is into integration of second, and when you integrate the derivative, then the derivative operator vanishes, mean f prime will vanish, so you will be left with ft only. And since this term is integrated, you should apply the limits of integration minus t0 to infinity, then integration of second, this integration mean operator dt. Okay, integration of second, this means again ft into derivative of the first factor or first function, and this is an exponential, and the derivative of the exponential is the exponential, so as it is, into derivative of the exponent, mean power of e. Okay, this, and this derivative with respect to t will be minus s. Now we should apply the limits. first upper limit minus the lower limit. Okay, this minus and this minus is plus, and s can be taken out because s is not a t. T is the variable of integration, and other than t everything is constant and can be taken in front of the integral sign, mean on the left of the integral sign. So it is s outside the integral sign, you can say also. T e to the power minus st into ft. Right? Now, look, this is this piece, which is I am putting blue. This is your Laplace transform operator for the limit t0 to infinity. And here, e to the power minus infinity is 0. And this will be 0 only when s is positive. Because positive s multiplied with negative will be minus, and that minus means minus infinity, and e to the minus infinity will be 0. So this will be 0 only when s is positive. This we will describe in the end. 0 into f infinity minus 1 e to the power 0 is 1 into f of 0 plus s into, this is your operator L, mean Laplace transform operator, and it is acting on ft, so its action is written with the curly brackets. So L is acting on ft, mean this is the Laplace transform of ft. So as in equation 1 you have Laplace transform of ft, you have something like this here with some additional terms. Let us simplify them, and you have, this is 0 minus f0 plus s into L of ft, right? And you should mention over here this 0, that s is greater than 0. Mean s is a variable which should be greater than 0. And this 0 multiplied by this 0 mean this f infinity is finite. And if infinity mean value of the function at infinity, it should be finite because f is a differentiable function. So the function which is differentiable will be continuous, and continuous functions have always finite values. So you should mention here, because f infinity is finite as f of t is differentiable. Okay. Now, on the left hand side you have L f prime t or L of d1f by dt 1. And next you have L of, Laplace transform of d1f by dt 1, and this is Laplace transform of f prime t, and this is equal to, write this term first, s term, which contains Laplace transform ft and minus f0, and you may name it as equation number 2. Now you need to find Laplace transform. Now I write it. N equal to 2 implies you need to find Laplace transform of d2f by dt square. Look, n is 2, then this means this thing. Now there are two options. You evaluate this as we have done the case for f first derivative, or you can iterate this equation 2. And iterating the equation 2 is more simple and efficient and fast. Okay, so let's do this. It is Laplace transform of f double prime t, and when you iterate equation number 2, look, iteration means use the rule defined by equation 2 for finding other Laplace transforms. And what's the rule here? This is first derivative and it transforms into zeroth derivative. So order of the derivative is one less on this side. And there is s. Use this here. S into Laplace transform of one order of derivative less. It will be f prime minus whatever you have here, that is here with t0. So whatever you have here, that will be here but with t0. So what you have done? Iteration, mean iterating the equation 2. Mean the procedure or rule defined by equation 2 has been used for writing the Laplace transform of the second derivative. Okay, now if you look at this, you have LF prime t, and here is LF prime t in equation number 2. Now you use the equation number 2. First you were using rule defined by equation number 2. Now you are actually using value from the equation number 2. So for this case, using equation 2, let's use it. Equation 2, Laplace transform of double derivative or double prime, and this is equal to s into L of f prime, this is equal to this thing, s into Laplace transform of ft minus f0, bracket close, this thing, and this minus f prime is already present over here. Now expand this bracket, mean distribute this s over these two terms. It is s square into Laplace transform of ft minus this s into f0 minus what is this? What is this? This is okay. This is minus f prime. Okay. This s will multiply here, and this term will be left. Or you can write this equation as, look, you can write here as s with the minus sign. There is a minus sign, this minus sign. Look, the exponent of s is reducing by 1. So in the end you will have s with exponent 0. Now, this will be helpful for generalization to the nth derivative. So this is d2f by dt square and L of f double dash t, right? You may name this as equation number 3. And we might be interested in the derivative Laplace transform for the third derivative, and that can also be found as we have found the double derivative. Let's check. And for n equal to 3 implies Laplace transform of the third derivative, right? And 3 here now. And this means Laplace transform of f triple dash, right? And as you have done already, you can iterate the equation number 2 again and use this rule that one order of derivative is reduced. So what you will get, okay, here you go. Use this rule, s into Laplace transform of the function whose order of differentiation is 1 less than here, and here is order 3 and here you will have order 2. right? And minus whatever you get here, that is here with t0. Now you have here this minus will be the same f double prime but t0, right? So this is the iteration. Please mention iterating equation 2 again. We have done this iteration of equation 2 twice. One earlier here and one time here. Now, this is LF double prime, mean Laplace transform of the double prime, and we have found it already in equation number 3. This is LF double prime. This. You can substitute this here. Let's do this. Using equation 3, yes, using equation 3, and let's see what we get when using equation 3. Let me erase it. And I think I can write the step over here, and then the last step will be written over there. Now, this is, perhaps there is a space here with me. I may write here. Equation this. Whiteboard needs to be used carefully. So, using equation 3 here. On the left you have Laplace transform of d3f by dt cube or L of f triple prime t, and this is equal to s into LF double prime, this LF double prime from equation 3, and you use this thing. It is s square into Laplace transform of ft minus s into f0 and minus s0 into f prime 0, right? This is for LF double prime, and in the end you have minus f double prime 0. Now expand this, mean distribute this s over each term within the bracket. This is s cube L of ft minus this is s square f of 0 minus this will be s1 into f prime 0, and this is minus f double prime 0. Since again the exponent of s is reducing by 1 each time, and in the end you will have again s with exponent 0, and on the left you have Laplace transform of f triple prime t. This is just for the sake of completion of the step, mathematical step, and you may name this as equation number 4. Now, pattern should be visible. When n is 0, there was only LFT, and when n was equal to 1, then there is this is for n equal to 1, mean first derivative, and there is LFT with some s, and in equation number 3, second derivative, Laplace transform of the second derivative, there is again LFT with s power 2, right? And in the end equation number 3 is s3 and LFT. Now LFT appears each time, and when you generalize, then LFT will appear again, but there is s. If it is of first order, then multiplied with s power 1. Second order, this is second order, equation wise 3 number. Second order, then there is s square, and when you have Laplace transform of third order, then there is s cube, and when you will generalize to nth order, then there will be Sn. into LFT. So let's generalize. So on generalizing, we get here. On generalizing, we get, here you go, L of dnf by dt n, that means L of fn t, this n for nth derivative, and this is equal to third derivative mean s cube, as I have explained. So here you will have Sn into Laplace transform of ft, because LFT appears in equation number 1, equation number 1, in equation number 2, and in equation number 3, this, and then in equation number 4. Now, what's the pattern next? The exponent of s reduces by 1 each time. And when it comes about the reduction, then each sign is a negative sign. So you will have here minus, reduce the exponent of s by 1, it is n minus 1, into. Now it's a story about these negatives. This s, here is no derivative over here, means zeroth order derivative. Then this is first order derivative, this is second order derivative. So as you go next on the right, the order of derivative increases by 1 unit, but exponent of s decreases by 1 unit. So the starting order of derivative for the f is 0. No derivative means the zeroth order of derivative. So you will write here zeroth order of derivative, right? And then reduce this exponent of s by 1 and increase this order by 1, right? Minus one more term, reduce the exponent of s by 1 and increase the order of f by 1, and instead of placing prime and double prime, I am putting 1 and 2 so that counting becomes easy. Okay, minus dot 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 and last term with also of course minus sign. And what will be the last term? The exponent of s keeps on reducing and goes to 0. The same will happen over here. S will be 0 and the exponent of s keeps on increasing. Look from here. This increases from f0 to 2 and the derivative is 0, derivative is 1, derivative is 2. So derivative increases to 2 and the exponent of s decreases from 2 to 0. So the same thing here from the negatives, from this point. The exponent of s is decreasing to 0. The order of derivative of f will increase to this number f n minus 1. Okay, this is visible from here. Look, the exponent of s is 2. It is decreasing by 1 unit to 0. Same here, decreasing by 1 unit to 0. Now order of derivative. 0 order of derivative, first order of derivative and second order of derivative. Mean order of the derivative is increasing from 0 to 2. And this 0 to this n minus 1. Right? Now, you have generalized the result for nth derivative, and this can be written in a closed form as well, mean in the summation form. And let's check how is it written. You maybe you may decide to leave this as such, but it will be more interesting and advisable to express the final answer in the form of a summation, because this is the summation. L of nt is equal to Sn into Laplace transform of Ft, and minus is common from all the terms, minus, then there is the summation sign, and s, and exponent is n everywhere, you will write n, and this is changing 1 2 3 so on. So this changing index is I, and I is from 1 to n. I is from 1 to, and when I is 1, then n minus 1 here. When I is 2, then it is Sn minus 2, this term, and so on. Now, you need to multiply with order of the derivative of f at 0, and the exponent will be what? This is 0. So it means this is I minus 1. The exponent, mean order of the derivative should be I minus 1. Why? I is equal to 1. This gives Sn minus 1 here, and this 1 minus 1 will produce 0. And when I is 2, then this is Sn2, Sn minus 2 this, and this 2 mean 2 minus 1, 1. F1 mean first order of derivative, which is F1 or F prime, whichever you like. And in the end, the last value of I is n. Substitute this n. Then n minus this is n, and n minus n will be 0, this one. And this n will be Fn minus 1. N minus 1, right? So you can express your result in this form of summation, right? And this is your final answer for the Laplace transform of the nth derivative of the function, which you can write in this notation or in this notation. And what is the answer? The order of derivative is the exponent of s, which is the new variable in the transform, and then there is a Laplace transform of ft minus this sum, right? So keep practicing this. I hope it should make you enable for having a good grip on taking Laplace transforms of the derivatives. Thanks for watching. Keep watching, and please like, share and subscribe this channel with your friends and family, so that such kind of detailed videos comes to your inbox in the first place. Thanks for watching.